Hello, today we're going to solve a very beautiful integral, and we're actually going to use a lot of trigonometry, which is definitely not necessary, but I think it's a nice solution to get this into finite bounds quickly. And maybe the first hint for doing that is the a squared plus x squared, which definitely reminds us of some arctan kind of antiderivatives. So let's see how we can use that to our advantage and as a hint to solve this integral quickly. So first of all, we can make the substitution inspired by our arctan antiderivative. X equals a times tangent of theta. Now, let's see what that does to maybe log of x first. So we take the log of both sides, which means that we get log of x is equal to the log of a times tangent squared, but using log rules, we can say that that is equal to log of a plus log of tangent of theta, right? So let's see what that does to dx as well. So dx is going to equal a times secant squared theta d theta, right? Okay, nice. So we've got almost everything set up to do this substitution. Maybe one more thing we should think of is our bounds. So when x is equal to 0, tangent of theta should be equal to 0, which means that theta has to be equal to 0 as well. So we go from 0, and then we go to up to infinity, and that means that tangent of theta has to be equal to pi over 2, right? And then next we can write log of a plus log of tangent of theta. And we can also write, maybe let's factor out a squared before we substitute that in. So a squared times 1 plus tangent of theta squared, right? And then the last thing to think of is dx, which is going to be a times secant squared theta d theta. It looks a lot more complicated right now, but let's first of all get rid of this a squared and this a. And then something else we can use is, let's see, sine squared of theta plus cosine squared of theta is equal to 1. And if we divide that by cosine squared of theta, we get tangent squared of theta plus 1 is equal to secant squared of theta, right? And we can use that in this situation nicely to reduce this part here, so this part, and this part immediately. So we can divide those two parts and we just get times 1, right? And so we've now got this integral, which is actually quite simple to solve. So first of all, we have got two different integrals we can split up here. So we're going to get the integral from 0 to pi over 2 of log of a divided by a d theta plus a second integral I. And I'll calculate in a moment. Okay, nice. So maybe let's quickly calculate this integral. Notice a is just a constant, so we just get pi over 2 times log of a divided by a. So we're going to get pi here and 2 here. Now let's calculate I. So I is equal to the integral from 0 to pi over 2 of the natural log of tangent of theta divided by a d theta. Let's see what we can do for this integral. I've actually solved some very similar integrals before. So maybe if you want to learn how to do these things more consistently and see these quickly, you can look that up. I've done something with log of cosine with similar bounds as well. So let's see how we do this. First of all, maybe let's get rid of this dividing by a in the integrand. I think that's unnecessary. And now we'll make a substitution that is very common for these kind of integrals. We're going to make pi over 2 minus alpha equal theta, and that also means, using some algebra, that pi over 2 minus theta is equal to alpha. And we also get that d theta equals minus d alpha, right? And one more note before we make this substitution. You might remember from like trigonometry classes that pi over 2 minus theta is just going to be cosine of theta, and the same holds for cosine if you plug that in. And of course, if we apply that to tangent, we just get cotangent, right? So let's see, 1 over a, and then the bounds go to pi over 2 and 0 just by plugging theta in there, and we get log of cotangent of theta, but in our case, we're going to write that as tangent of theta to the minus first power, not the inverse tangent in this case, just to the minus first power, and it's obviously not theta, has to be alpha times minus d alpha. Okay, now we can use this minus sign to switch the bounds of integration again. So we're going to get 0 to pi over 2. And then we can also use some log rules to just bring this minus first power in front of the integral. And now we can see the simplification unfold. We just get that this integral is equal to minus I, right? So that means if we read from the complete left-hand side of this line of equations and the complete right-hand side, that I equals minus I, or in other words, 2I is equal to 0, which means I is equal to 0. And that means that the solution we get in the end for our integral from 0 to infinity of log of x divided by a squared plus x squared dx is going to be equal to log of a times pi divided by 2 times a. So we used a ton of trigonometry there, which might have been unexpected seeing the log there. Most of the time when you see exponential stuff or inverse exponential stuff, that doesn't really work. But we used it inspired by the a squared plus x squared, and we got a really nice answer quickly by just using mostly clever tricks and substitutions. Didn't even use integration by parts. So thank you so much for watching. Until next time, if you got any tips for me, please subscribe as well. Till next time.